Thank you. Good morning and thank you to the organizers of ESBEST 2026 for this opportunity. My name is Catherine Karina Corona Reyes from the Facultad de Ciencias Químicas at Universidad Autónoma de Coahuila. On behalf of my co-authors, I am pleased to present our work, Plasma Activated Water from Different Water Matrices, Physicochemical Characterization, Antimicrobial Activity, and Regenerative Potential. Let's start with the problem. Antimicrobial resistance is one of the greatest health emergencies of our time. It was directly responsible for an estimated 1.270 million deaths worldwide in 2019 alone, according to Murray and colleagues in The Lancet. This urgency is derived the search for alternatives to conventional antibiotics. One promises candidate is non-thermal atmospheric plasma, a technology coupled for generating reactive oxygens and nitrogen species, such as hydrogen peroxide, nitrate, and nitrate, with well-documented antimicrobial and biological activity. When this plasma is applied directly to water, those reactive species dissolve and persist in solution, producing what we call plasma-activated water, or PAW. PAW is easy to apply in both biomedical and environmental settings. Prior studies show it can inactive pathogen microorganisms and promote tissue repair. But here's the key point: our study boils on the chemistry of PAW, and therefore its biological activity depends strongly on the water used to make it. So, your objective was to directly compare plasma-activated water milieu ultra-pure water against plasma-activated tap water, a mineral-rich matrix, across 4 dimensions: reactive species generation, physicochemical characteristics, antimicrobial activity, and in vitro regenerative potential. Then, to generate PAW, we use atmospheric pressure plasma jet operating in air discharging at 1000 Hz and 20 watts, with a nozzle held 2 cm from the water surface. 800 milliliter sample was continuously stirred at 20 RPM and treated for 15 minutes. We repeated this identical protocol for both milieu water and tap water, so that any difference we observed could be attributed specifically to the precursor water's conversion. When the ran broad characterization panel, temperature, pH, oxidation reduction potential, electrical conductivity, and the K-reactive species. And on the biological side, we assess antimicrobial activity against E. coli, S. aureus, and S. epidermis, using both agar diffusion and liquid culture inhibition assay, and we evaluate regenerative potential through an in vitro starch assay in dermal fibroblasts plus MTT, calceina M, and hemolysis testing. Here is our full physicochemical data across 4 conditions: untreated and plasma-treated milieu and untreated plasma-treated tap water. Speaking 11 parameters, I won't walk to every cell, but I want to draw your attention to a few rows. We come back to conductivity, ORP, pH, and the ESView count at the bottom. First, even before any plasma treatment, tap water's conductivity is roughly 26 times higher than milieu's, simply from dissolved minerals. Second, plasma treatment sharply rises ORP and hydrogen peroxide in milieu water, nearly a 5-fold increase in ORP, direct evidence of reactive species generation. Third, the two matrices diverge in pH. Milieu acidity sharply after treatment, while tap water stays alkaline buffered by its mineral content. And finally, one of the microbial side colonies account in tap water fall from 150 CFU per milliliter after plasma treatment, while milieu remains near steadily through in both conditions. Turning to antimicrobial activity, qualitative or agar diffusion assay confirms that both PAW types inhibition growth of three-test organisms. Quantitative or liquid culture inhibition data show that tap water PAU nearly eliminates S. aereus growth and strongly suppresses S. epidermis, while both PAU types are more modestly and similar effective against E. coli, consist with the added protection Gram-negative cells walls provide. Next, cell proliferation measured by calceina M fluorescence. Relative to unread controls, both monocytes and fibroblasts then upread after PAU exposure. Monocytes to roughly double the control signal, fibroblasts more modestly. This is consistent with the PAU reported rolling promising disease repair. That said, the statistical analysis grouped of these conditions under the same significant letter, so it describes this similitude thread walling up, not yet a problem, those depends of the effect. For cell migration or stretches say show both PAU types closing the one faster than the unread control from the very first time point. By 48 hours, that water PAU reached the highest closer around 66% ahead of milk PAU at both 59% and the control at 54%. None of the conditions reached full closure within this window, but the acceleration is clear and consistent. No, hemolysis. We tested both PAU types across concentration range from 0 to 100%. Hemolysis dose trend downrun as concentration increased for milk PAU from about 100% down to 73%. But every single condition we tested across both matrices and all concentrations except the roughly 5% result that ISO considers not hemolytic. Then in MTT, monocytes viability drops sharply between 24 and 48 hours at every concentration tested for both PAU types. Fibroblast viability, by contrast, stay comparatively stable across both time points and the full concentration range. So different cell types appear to tolerate sustained PAU exposure quite differently. Monocytes like more sensitive than fibroblasts. Then in discussion, putting this all together, milk PAU lends toward an oxidative antimicrobial profile, higher peroxydiroxane and higher ORP, lower pH. Tap water PAU lends toward regenerative profile, nitrate-rich, alkaline, and with the stronger one healing performance we measure. So precursor water isn't just a technical detail; it's a tunable designer parameter you can use to steer PAU toward a specific therapeutic goal. To conclude, precursor water composition critical shapes both the physicochemical and biological performance of PAU. Milk water yields a more oxidative, other hydrogen peroxide rich PAU. Tap water favors nitrate accumulation and stronger regenerative activity. Both formulations show real antimicrobial and cell proliferative effect, but hemolysis except the ISO threshold at every concentration we tested, so hemocompatibility needs further optimization before any clinical translation. Overall, we see precursor water selection as a viable, low-cost lever for tailoring PAU to specific therapeutic application. We use this reference. And thank you very much for your attention. I'd like to commend Universidad Autónoma de Coahuila, Universidad Autónoma Agraria Antonio Narro, and all of my co-authors and collaborators who made this work possible. I'd be glad to take any questions. Thank you.